So let me dive in. So first of all, my group, I'm really grateful. I've been extremely lucky to have excellent students, and I think this is something that at Weizmann we really have. So there are two efforts in my lab. One is collisions done at cold temperatures. Another group of students and postdocs are pushing towards ultra-cold regime. So these guys are doing collisions. These are hoping to see collisions. This group was led for a long time by Yuval Shagam, a brilliant student. Now he's a postdoc at Gila, Cornell, trying to measure electron dipole moment. Now this group is led by Martin and Yair. And most of what I will be talking was done by Nitzan. He was a postdoc again. I was extremely lucky to have him in my lab. And a lot, I must acknowledge Julia. She's my wife, electrical engineer. And you will see how important this combination of science and new technologies. So what I will tell you about will be a simple story. I want to show you what type of collisions can we do, where we want to go. And again, the deal is what we are doing it with molecules and not with atoms. So what we will be seeing, few things. So first of all, I want to show you quantum effects that happen at very low collision energies. Second, the more interesting thing, how molecular degrees of freedom change interaction properties. So atom-atom collisions we understand very well. What happens when one of the atoms becomes a molecule? Different, not different, how does it change? All of that knowledge and intuition that we gain really leads us towards our dream project of trying to reach quantum degeneracy, again with molecules. And again, what I want to sort of take home message, what we are able to do in our lab is precise quantum state resolved collisional energies, collisional experiments really pushing towards this deep quantum regime. Oops, that I don't need. Okay. Can we switch off interesting. So, actually what I want to show you in 3 simple pictures. Too complicated. Okay. Are we on? Oh, great. Thank you very much. Much better, yeah. Super. So, really what I will tell you, there are 3 parts to my talk. We will start with the classical collisions, we will go into cold collisions, and we will go at last slides into ultra-cold. What changes between these 3 slides is de Broglie wavelength. So here you see red little dots colliding, right? So this is a classical hot gas. Simple thermodynamics will tell you the story here. We're going to cold, so sub-Kelvin temperatures. You see that these atoms become wave-like, so quantum effects become important. And finally, this collapses to a new state. So this is a Bose-Einstein, for example, condensate. So you see that now a number of particles are defined by a single quantum state. So we want to go from here to here. Now what you see here is a little red dots. Or not just a little red dot, it's an atom. And it's a particular atom. Which atom is that? It's rubidium. Why rubidium? Because it's the easiest atom to control. And how you control that? You laser cool. You use photons to cool atoms from room temperature even higher into nano-Kelvin regime. So you control from room temperature down to nano-Kelvin, so you span orders of magnitude in energies by interaction with light. So this simple effect, this is interesting, oops, I'm sorry, technical problems. That's new, so first time Apple crashes on me. So what I would argue that laser cooling really brought a revolution to the field of atomic physics. And what we are trying to do is to extend this revolution and to bring the same beautiful physics that has been done with ultra-cold atoms to do the same with molecules. Now, why molecules? So when you think about it, why molecule is different? And what can you do with that? So this is quite amazing for me, at least. If you look, what is the most precise now measurement of electron dipole moment? It has been done not on an atom, but on a molecule, on a cold strontium fluoride molecule. So I think this is really amazing. The highest precision for something that we don't even know if it exists or not. So how molecules are different in a fundamental way from atoms. So first thing, of course, what you have to change the interaction. Interaction becomes angle dependent. It's anisotropic. And this is completely clear. Molecule any molecule will at least have a quadrupole moment. And this quadrupole moment will change interaction. Are we sensitive to this interaction or not? I don't know. How do I probe that? What is the degree of freedom that I have to look at if I want to see if an isotope is important or not? Is rotational degree of freedom. Why? It's completely clear. Molecule spins and it samples different interactions. So an isotropy is sampled by rotational degree of freedom. To put it in mathematical language is extremely simple. So I can take my interaction and express it in two terms at least. One term, this is an atom. So you see this is isotropic part of interaction, doesn't depend on angle. And I put everything that depends on angle as at the first order in an anisotropic part of interaction. Now, molecules, which molecules we will talk about. So we will make it simple. It's in our last talk of the session. We have to be here slow. I will speak about hydrogen. Hydrogen is nice. Why hydrogen is interesting? First of all, you have a lot of that, and you have a lot of hydrogen which is cold. We're in interstellar space. So a lot of reactions start with molecular hydrogen. But molecular hydrogen is a funny molecule. It exists in two distinct states. You have parahydrogen and orthohydrogen. So what is orthohydrogen? You have to look inside into nuclear degrees of freedom. So in orthohydrogen, nuclear degrees of freedom, two spins are aligned. What does it mean? It means that the nuclear spin wave function is symmetric. But don't forget that the nucleus is a fermion. Two fermions cannot sit one on top of the other. If I would take orthohydrogen and let it live in the lowest rotational state, I would violate this principle. How nature solves this problem? In a beautiful way. It actually deletes all even rotational states. So the lowest rotational state for orthohydrogen is actually J equal to 1. It's rotational excited. Completely different species is parahydrogen, and both actually exist in interstellar space. It has antisymmetric wave function, which describes nuclear spins, which forces the lowest rotational state to be ground state. So here we are, the simplest molecule and a beautiful complication, but also beautiful degree of freedom. Why? Because in my lab I can do two experiments. One with mixture of ortho and para, where 75% simply because of statistics is in rotational excited state, and I can prepare a pure J equals 0 state of parahydrogen. So two experiments, I can tell you exactly what happens with rotational ground state and rotational excited state. Why do you want to do your experiments at cold regime? You want to see quantum effects. What type of quantum effects are nice to see? Resonances. What are resonances? So resonances come from interaction, which is given by nature, and the rotational degree of freedom. What is this rotational degree of freedom? It's a simple centrifugal repulsion. So you add attraction with repulsion and you form at large separation centrifugal barriers. Now these barriers we can tunnel through if our collision energy is exactly equal to this state energy. Another type of resonance can happen if we transfer the energy between degrees of freedom. This is a classical variant of a similar thing, so I will not talk about that. What is cold, you also have to realize that temperature, absolute temperature is not a good measure. What you need to think about is how many quantum states participate in collision. And here I put you three different types of interactions, three types of different experiments, all probing the same physics, where only a very small number of quantum states are available during a collision. But you see that the absolute temperature goes from nanokelvins up to kelvins. So strong interaction. You see this quantum physics happening at very low temperatures. You are pushing to much lighter species with very low polarizability, and you have exactly the same effects, but much higher temperatures. And these Kelvin temperatures are extremely convenient for us because this is exactly where we can hit it with our experiments. Cooling. Why cooling is so challenging? So first of all, I need to explain you why cooling is much easier on atomic species. How does it work? What you do with cooling, by cooling atoms, you exchange atomic momenta, linear momenta, with photons. So you have to scatter a lot of photons from an atom in order to stop it from hundreds of meters per second. What does it mean? What does it mean to scatter many photons? It means that we have to go through many cycles of absorption and spontaneous emission. Absorption, spontaneous emission. We have to have what is called closed cycling transition. Now, as chemists, you immediately realize that this is extremely difficult to do with molecules, to replicate exactly the same scheme. Why? Because, of course, this electronic ground state is split into many vibrational and rotational states. Nevertheless, there are quite a few groups that are trying to do this exact cooling. And just to give you a flavor, so the lowest number of different lasers that you need to access a single molecule is 7. The highest that I know is 15. It's a really complicated way to do it. So we are in a different camp. We are looking for a much more general way to cool molecules. We don't touch lasers. Although I spend half of my budget on lasers, still, we want to be as possible as general. How do we do that? Use a very straightforward way to cool, something that you use in your refrigerator every day, expansion. This is our device which we took from Uzi Even, developed by Uzi. So what is it? It's a simple solenoid which releases gas from high-pressure reservoir into vacuum. So what do? We generate very high density cloud. This cloud expands and adiabatically cools. Why? Because there is no interaction with surroundings. How well does it cool? It's absolutely amazing. So I can start with room temperature. So this is room temperature helium velocity distribution. You see Maxwell-Boltzmann broad distribution, and it collapses to this delta function. How cold this may be, it can go to 50 millikelvin. So it's really free lunch. You start with room temperature, you end up with millikelvins. What is the beauty of this method? That you not only cool the motional degree of freedom, but you also cool by collisions internal degrees of freedom, which is extremely difficult. So vibrations and rotations we can freeze to ground state. And that's beautiful. What is the price that we pay? Oh, of course, no free lunches. So this bunch that is generated in our valve is extremely cold, but in a moving frame of reference. So this cold, you see this delta function, doesn't sit in zero, unfortunately. It's shifted at very high velocity. So for helium room temperature, it's almost 2 kilometers per second. That's one problem with this source. Another, actually, you would think it's quite dilute, right? We are letting gas expand into vacuum. You know, what will happen? But actually, if you are trying to go from one chamber to another, and you hit any wall, room temperature wall, you see that you generate these beautiful shock waves. So these sources are not as benign as you would think. And even after 50 years, Yair Segev and my group was able to solve this really annoying problem that nagged our experiments for years. And now we can increase the number of molecules that reach our experiment by order of magnitude. So really interesting. Old technology, but you can still find new and interesting games that you can play. So, sort of to sum our cooling, what can we do? We can internally cool aerosol molecules easily under 1 Kelvin. We gain in the mean velocity, so our temperature, center of mass temperature is much more than 100 Kelvin. And our densities are actually quite high. So you can reach densities 10 to the 14, right? So for you, it's vacuum. For me, it's really quite high density. How do I know? Well, you hit the wall, you see shock waves, it's dense. Now, how do you solve that problem? So again, beams are here for more than 50 years. And many experiments were done with collisions. So you take two sources, let them collide at different angles. You can tune this way collision energy, and you can go even down to quite low collision energies. How low? Lowest that people were able to do was 5 Kelvin. Why? Because you cannot place these two sources too close together. As you saw, we generate shock waves and destroy each other. So there's no game there. So really, for 50 years, 5 Kelvin was as a concrete wall. Now, how did we solve this problem? Well, we went around it. So there are two ways to think it, right? So if velocity is the problem, one way, and this is what most of the people thought, would be just to decelerate our beams. But that's expensive. You will see later. We solved it in a different way. We moved into the inertial frame of reference. So instead of colliding two beams, we take two molecular beams. One of them we just let in a straight line, so we do nothing. But the second, we deflect. How we deflect? We need force. We use magnetic fields. So we deflect it, and after this deflector, what we see two bunches riding at kilometer per second velocities. But both velocities are matched. So our collision energy is only limited by the standard deviation of velocities at the point where we measure collisions. And that can be extremely cold. So by the simple trick, we lowered collision energy by 3 orders of magnitude. And that really brought us from this classical regime deep into quantumness. So, what do we use? We need force. We use Zeeman effect. This is a spin 1/2 Zeeman effect, right? Very simple picture. Unfortunately, Zeeman effect is not too strong. So if you take 1 Tesla, which is quite a lot, and you calculate how much Zeeman shift you apply, it's only 1 Kelvin. And you remember we are hundreds of Kelvin hot. So what do? We need extremely high magnetic field gradients. Now we are lucky. We don't need these magnetic field gradients to be continuously on. We have to be on only until our small bunch of atoms or molecules passes through this magnetic deflector. So our magnetic field is on only for 300 microseconds. We pulse a lot of current through these simple, copper wires, and we generate fields up to a few Tesla. That is enough to deflect a paramagnetic particle flying at 1 kilometer per second. How does it look? So this is how our apparatus looks. So this is actually for those who are in theory. I was actually a theorist. So this is a machine which is able to diagonalize a Hamiltonian with 4 electrons and 2 degrees and 3 nuclei. So this is my apparatus. I will not tell you too much. So there are a few parts. What do? So let me start and show you that we are already reaching quantum regime. How? Well, let's look at the simplest process, elastic scattering. Let's take 2 species, metastable helium, this is my small magnet, and neon, 2 atoms, nothing special. So I let them collide, and I look, right? I have to look, I want to see the products of this collision. How do I look? I look with velocity map imaging. What is velocity map imaging? It's a very nice device which focuses same velocity ions onto a single spot on a 2-dimensional detector. So this is my detector. I look from above, I see a single spot, and I know that this comes from ions distributed in very large volume, but we have exactly the same velocity within the deviation, standard deviation of 10 meters per second. Beautiful. That's cool. Now, let us collide. Okay, so we start with our atom that we measure, and now we come with another atom hitting it at 200 meters per second. So this is about 10 Kelvin. What will happen? What I expect that I will see products flying at the same, it's elastic scattering, 200 meters per second in random directions. What does it mean? So I should see now a ring on my 2-dimensional surface. What do I see? I see the structure. I see beautiful stripes, interference pattern. Where does that come from? Well, this is diffraction. So exactly the same way as light diffracts from opaque sphere, and you see these beautiful airy rings, the same way particles that behave as waves diffract and form, again, this beautiful angular distribution, which has been first observed in a beautiful experiment by Udo Buch. Bas van der Meeracker did beautiful also experiments looking at this scattering with the VMI detector. So that's the simplest possible experiment. And you already see, even elastically, we are beautiful in a quantum regime. Now, let's go to reactive scattering. What is our reactive scattering process? It's spinning ionization. We have metastable helium. It's a nice atom. First of all, it's paramagnetic, and it has 20 electron volts of internal energy. It hits hydrogen. Well, it doesn't matter what it hits. If ionization potential of partner is smaller than 20 eV, we have open channel for ionization. So I will be forming H2 plus ions, which I can count. So I need at least 2 potential surfaces to describe this really highly non-adiabatic process. So incoming channel has 2 neutral particles, metastable helium and H2. They collide, and we have exponential probability as a function of internuclear distance to ionize. So electron will be emitted, and we end up on ionic potential surface. So 2 potential surfaces at least. There are several flavors of this process. We can control it. We can do our collisions with metastable helium in triplet state, which has a lifetime of 8,000 seconds, or we can do our experiment in triplet P state. One is slow, one is fast. What's fast, what's slow? Fast process means every collision leads to ionization. Slow process means, well, every 1 out of 100 collisions leads to generation of H2 plus ions. I will skip the fast part, although it's really interesting. And we'll go directly to the slow part, so to quantum. So let's do the experiment. Let's merge two beams and change relative velocities or collision energies. What do we see? So first of all, what do we see? This is collision energy. 1, 2, 3, 4, 5 decades of energy in a single experiment. This is, on logarithmic scale, our reaction rate, how fast we are counting our H2 plus ions. This is the end of a classical regime. You see nothing interesting, just a boring line, but you see at 2 Kelvin, at 200 millikelvin, very strong peaking. Where does that come from? So actually look, at 200 millikelvin, our reaction rate is as high as at room temperature. Really surprising. First time we saw this result, we were so surprised that we tried to find what is the mistake that we made. But there is no mistake. So what are these nice peaks? These are the quantum resonances. So these are quantum scattering orbiting resonances that are able to find and pinpoint with extreme accuracy. Now you would say, okay, this is completely clear, and you can also see the same effect with atoms. And that is absolutely correct. Do atom-atom collision, you will see exactly the same. Well, they will appear in different energies, but of course they are ubiquitous to any cold collision. What is special about molecular degrees of freedom? Well, let's try. As I told you, we can separate two rotational states, ground state and the excited rotational state. So we start our experiment, I go collision energy, reaction rate, and you see from 300 Kelvin down to, well, 10 Kelvin, there's absolutely no difference. And classically, this is completely clear. It doesn't matter. Think about our hydrogen. Let's start with J equals 0 state. Well, I have equal probability to collide with metastable helium at any orientation. Now let's start spinning. Well, I have exactly the same probability, absolutely random, to hit metastable helium. And this is exactly what you see. So both of these H2 molecules behave exactly the same in the classical hot temperatures. No surprise. Let's go to quantum regime. Under 1 Kelvin, well, the picture is completely different. You see that one of the strong resonance that we observed actually is coming only from rotational excited molecule. So when you enter the quantum world, that's it. These two molecules are absolutely different species. Now, this is what Nir mentioned. So let's now play the game of experiment versus theory. So if you come to theory colleagues, and we actually have beautiful collaboration in the theoretical part led by Christian Yakov from Kassel. And let's say, well, calculate. Right? What do you need to do to calculate our results? First of all, you need interaction potentials, so you need to do ab initio calculation, and you need to do molecular dynamics. Well, we all know that we are excellent in that. So if you go and do the highest accuracy ab initio calculation, so this is coupled cluster, SDTT, including triples, you get the green curve. So actually, funny enough, the classical, we didn't draw it here, but you see that the classical range is beautifully reproduced by the sphere, no problem. But the position of resonance is absolutely wrong. So our colleagues really have to do many corrections, including to try to include full configuration interaction. So a lot of games to try to reproduce the results. Nimrod Moiseev is doing also an interesting study now, trying to calculate reaction rate itself from first principles. So again, it's quite a complicated problem turned out to be. So when you think about it, what do we have on our hand? We have now a method which does not include a single laser. And we are able to find states of free body interaction with a precision of 200 megahertz. So we're doing really, it's nearly spectroscopic precisions without a single laser. Even better, if you think about IR spectroscopy, right? You usually probe a very small volume of a phase space. We probe the whole, everything from short range to the long range. That's the reason that's so hard to reproduce. Why there is a difference between rotational states? Let me give you just a very simple explanation. All you need to think is to take the potential which has two parts, isotropic, which doesn't depend on angle, and anisotropic part, and calculate the expectation value with different rotational functions. Okay, so this is first order perturbation theory, nothing more than that. If we have hydrogen in rotational ground state, we average out the anisotropy to 0. So for weak anisotropy, H2 molecule in ground rotational state, it's not a molecule, it's an atom. It's a symmetric object with mass of 2 atomic mass units. Let's go to excitation. Now, excited rotational states far away is triply degenerate, right? What does anisotropy do? It mixes these 3 states, produces 3 new states, and one of them, you see, actually, what does it do? It pushes the potential up. So if you had a bound state close to the dissociation threshold, this anisotropy will push it up, and now we will be able to observe it in our collisional experiment. So for this here, in this potential, for example, we are dark, we don't see anything, it's a real bound state. Here it's a resonance state, it's quasi-bound, and we're able to see them. Why we are so bent on precision? You would say, come on, you build a nice machine that diagonalizes Hamiltonian. Okay, well, I will answer you why we need that precision. The second experiment, really with our dream to generate molecular Bose-Einstein condensate, absolutely depends on precision that you are able to give in calculation. Why? And here we have to go a little bit deeper. And the question is, how do you cool? Let's say I spoke about laser cooling of atoms, laser cooling of molecules. But eventually, the last step before condensation in 99% of experiment is done by evaporation. So unfortunately, I cannot demonstrate because I was not allowed to bring a cup of coffee here. Otherwise, I would. So how does evaporation work? And these are 2 beautiful experiments that really led us to this idea. This was done by Dan Kleppner. So one of the first condensates was done with atomic hydrogen without laser cooling, just by evaporation. So what's evaporation? You hold your hot particles. So Dan Kleppner was holding atomic hydrogen at 100 millikelvin. And what you start, you release the hottest atom. How do you do that? Well, you just cut them, right, by height. You cut in Maxwell-Boltzmann distribution the hottest part, and you weigh. Rethermalization, you cut again the hottest part, rethermalize, and cut. Well, exactly the same way as your cup of coffee cools down. Now, this process critically depends on collisional properties. What do I mean? There are 2 types of collisions that can happen. And this I took from some paper, PRL paper by Hudson. What do you see here? You see cross-section for collisions as a function of a parameter. So this gentleman simply took a potential and scaled it by, plus minus 5%. So there are good collisions. What are good collisions for cooling? These are elastic collisions. They thermalize. So this is the good. There are also bad collisions. What are bad collisions? These are inelastic collisions. Why they are bad? Best case, I just lose a molecule. Worst case, I will heat. And this is the ugly. So you see, what is this regime? You see that if you, in this particular range of scaling of potential, you see that our probability of elastic and inelastic process is exactly the same. What does it mean? I have 50% of chance to collide elastically, to cool, and 50% of chances to lose. You need about 4 collisions to thermalize. You can try it on a billiard table. 4 collisions already thermalizes. So this is absolutely killer. So here you are. Here's a paper appearing, in a nice journal. And I'm, what do? I'm experimentalist. Do I build the experiment here or not? So is it a prediction or not? It's really absolutely a key. So think about it. Now we are running in complete darkness. We are building experiment. We will do collisions, but we absolutely don't know what will be result. It can be either champagne bottle, right, BC, or a wasted, or nicely invested PhD. So that's why precision is absolutely necessary for us. It's not a game, it's a must. Again, how do we want to cool? As I told you, we need evaporation. But remember, our source is actually quite annoying. Our source of cold atoms and molecules is moving 1,000 meters per second. I cannot evaporate that fast-moving beam. Why? I don't have time. Collision frequency in our cloud is on the order of 1 hertz. Our experiment, collision experiment, is finished after a millisecond. Why it is finished? Well, our molecules crashed on the wall of our chamber. So if you want to cool by evaporation, first step that is absolutely necessary is to stop. And without that, you cannot run. How do you stop? Well, you build a box, right? How do you build a box? This is how you build a box. So hundreds of atomic physics experiments use a very simple setup called magnetic trap. So there are 2 solenoids. that generate magnetic field minima 0, actually, magnetic field, somewhere in the middle. So if you have now a small magnet, a paramagnetic molecular atom, it will be stuck in between them. So it will be confined in 3 dimensions. This is a static picture. I cannot load this trap from our supersonic source. Why our supersonic source? Energy is 400 Kelvin. Trap depth, well, best case 1 Kelvin. No way. So I have to decelerate. How do we do that? This is how we do it. So what you see here in our lab, this is a magnetic decelerator. It's a conveyor belt. So what does it generate? It generates a magnetic box of dimension about 1 centimeter cube, and it starts at few hundred meters per second and slowly decelerates to 0. How we do it? We have 480 of overlapping magnetic traps that translate field minima from the source into the static trap. So how does it look in a simulation? So you see these are overlapping magnets. So magnetic field, you see the minima, this light region moves beautifully and keeps our molecules inside. So this is a magnetic bottle filled with, in our case, molecular oxygen. What's the challenge? Well, again, go and build that. Usually simple ideas are quite difficult to realize. So the length of this device, again, why it's so long? Because the Zeeman effect is weak. We have 480 of overlapping magnets. It takes 2.5 meters to stop molecular oxygen from 400 meters per second to full stop. These poor traps were really just simple solenoids. And we pass through these solenoids, this is 1 centimeter across, currents up to 500 amps.
Oxygen or
Oxygen, O2, oxygen, what you breathe right now. It's a nice molecule, right? It's, again, a homonuclear, and it's paramagnetic. What can we do? So right now, what we are able to do, we are really able to build this magnetic conveyor that takes us from 400 meters per second down to 0. And this is already a signal. These are molecules sitting in a trap, which doesn't move anymore. It's 0 velocity. And we see signal decaying on the order of 1 second. So think 1 millisecond, this is the time that we have in our merge beam, and this is 1 second. So 3 orders of magnitude more time. To give even ourselves more chance for cooling, we can not only take molecules, we can also do mixtures. For example, lithium. Why lithium? An interesting story by itself. I will tell if somebody wants to know. So that's great. We have already trapped molecules at very high densities for us, 10 to the 10 molecules per cc. This is enough to see collisions, absolutely. What is not enough is time. Way too short. We need few tenths of seconds. How do we solve that problem? Well, we are switching to superconductors. Why superconductors? We want to have much better control. So right now, our magnetic trap is built of permanent magnets, so there is 0 control. We have them in, that's it, forget about it. So we are now using superconductors. We are building extremely deep traps. So this is how it looks right now in the lab. And we view the additional beauty of these superconducting traps that we can compress. What does it mean? So for example, what you see here, this is our trap. This is the trapping region. So it's around 3 by 3 by 3 millimeters. We can compress it. Well, again, superconductor allows you to raise current densities to absolutely enormous number. We can compress it by order of magnitude. What does it give us? Much higher collision rate. So we can raise our collision rate by a factor of 10. So really, I'm absolutely sure that we will see collisions. I'm sure we will see thermalization. Will we see molecular condensate? Depends on collisional properties, but I don't know. And current theory level cannot predict, which is a bit sad, but that's fact of life. So we will have to do. And again, the nice thing about our experiment that we can change. So if oxygen doesn't work, first of all, we can switch to different isotopes, which have very different collisional properties because of, again, different rotational structure. We can switch to different molecules. We can add atoms. It's not infinite, but we have many more ways to try different combinations. So that's the hard part, and again, why? Because precision is important in these experiments. So again, low temperature collision, precision is the key. It's the output of the experiment, but this is also input for future experiments. Okay, so let me stop here and thank our collaborators. Christiane Koch from University of Kassel is really a great collaborator. We have a lot of interesting ideas, a lot of discussions. Wojtek was her postdoc, did a lot of work with resonance calculations. Renji and Vitaly Averbuch are from the Imperial. They calculated the first reaction rates. This is not a simple problem, so how fast electron escapes. Piotr did the ab initio calculations, and Ad from Nijmegen is helping a lot with molecular dynamics calculations. Funding, and a lot, I must say, I'm really, it's so bad I cannot complain. But a lot of funding is coming from Weizmann, and I'm grateful for that. And thank you for your attention.
Questions? Yes. So these low energy collisions are really amazing. I would like to ask something esoteric in that respect. Can you push your experiment to such, let's say, low collisions that you'll observe also the appearance of retarded forces from the standard C over R to the 6? We will see suddenly C over R
so
to the 7.
Absolutely good question. So this has been done with atoms. We will be able to do that if cooling works. So again, we need to go lower. I would say, so what I didn't show were experiments that we are able to see higher orders. So for example, going to see a van der Waals interaction and to see the next order, which is quadruple, that's easy for us. But I think this is already, this is where we're comfortable. To go next, we need to drop by another order of magnitudes or 2 orders of magnitude in energy. If evaporation works, we will be there for sure. And that opens many, many more experiments. Interferometry with molecules, right? Clocks with molecules. So I think that would be absolutely amazing.
Yes, Sudan.
The reason that you're using molecular oxygen is it's a triplet signal stereo.
Exactly.
Paramagnetic hydrogen has a dipole moment as well, so it's
yes, absolutely correct.
1,000 times more magnetic field.
Yes.
Any chance?
If you give me a very long lab, then yes. So we
all the way to physics.
Exactly. So we start from chemistry. We dig a tunnel. Possible again if there is an absolutely. Let's say if you think of experiment, which tells that you need H2, right, trapped and extremely cold, we could think about it. Because again, now we can reach much higher fields. And this we do with superconductors. We were absolutely surprised. So I didn't tell about the story at all, but superconductors are not built for our applications. Because usually people use them in continuous, right, generation of continuous magnetic field. They're extremely bad for AC applications. If you try to switch it on, it will quench. We are using high-temperature superconductors because of exactly that reason. And we see that we can push them to absolutely enormous fields and switch them on fast. So I wouldn't argue that I can reach 1,000 Tesla. But if needed, 20 Tesla in a pulse, we could do. So again, we could start with very slow H2, maybe HD, let's say, or D2, and we could decelerate it, in tens of meters. So not a kilometer, right? So if there is a good reason, we can do that.
Let's have the last question. You.
Which are the best candidates to produce a molecular Bose-Einstein condensate? Is it OH or other molecules you think of?
Nobody really knows. It's, again, and the problem is that nobody knows what are the collision properties. And it's a funny story. So the first trial molecule was K-rubidium. It was done by Jun from Gila. And it was funny. So they built this experiment, and they realized that this particular combination actually is reactive. So there are many groups now exploring different paths. There are people who build molecules from cold atoms. They are really beautifully stuck now in absolutely strange problem. We are generating cold molecules, so for example, sodium with potassium, and we disappear in seconds. Nobody understands why. There are wild theories running in the field, which are, some of them are absolutely crazy. Now, there are people who are doing molecular cooling. We have absolutely the lowest temperatures. We reach 10 microkelvin. But the problem that they suffer from is numbers. So we have 10 microkelvin cold sample with 100 molecules. That's, again, a bit of a problem. Now there is a field that uses this deceleration molecular beam techniques that was started by Gerhard Meyer at Berlin. This is absolutely fantastic. So what you have, you can either use Stark effect or a Zeeman effect. So we like magnetic fields. OH, excellent candidate, can be done with both. June is trying to do, Genie is trying to do that. For us, we could try that as well. Other candidates, interesting candidates, are NH2. We can generate it in very large densities, NH radicals, so small radicals. And atoms, we can do mixtures, carbon, oxygen, nitrogen. Same lithium, sodium. But again, nobody, if somebody will tell you that here is a good candidate, yeah, tell him to call me and tell me. There is no good candidate.
So we have to end. I get signals. So let's thank all the speakers and Eddie in particular.